All right, so yesterday we talked about activators. We said that activated aromatics are things that have strong electron donors on them, or anything that's electron donating for that matter. And then the strong ones are the ones where you have an atom with a lone pair directly attached to the aromatic ring. So something like phenol, phenoxide, anisole, or aniline. Somebody did point out that anisole in the book he lists as a moderate activator, but he listed at the high end of moderate activators. Oftentimes books will list it as a strong activator. It's kind of at that crossover between strong and moderate. I'm fine with you putting it in either class. Moderate activators, on the other hand, have this competing resonance problem where they can donate electron density into the ring or pull it out of the ring, meaning it's going to be a little bit weaker. And then weak activators are only activating due to the fact that they have hyperconjugation. So now let's look at deactivators. Deactivators kind of follow the same trend of strong, medium, and weak. So let's make a list of our strong ones. The first one we already have seen is where you have a nitro group coming off of your aromatic ring. And why is this strongly electron withdrawing? Yeah, absolutely. You could kick up this pi bond and kick out electron density onto that oxygen. So in this case, it's pulling electron density out of the ring. There are no possible resonance structures where you can push electrons into the ring system. All right. The next one is pretty similar, where the nitrogen attached to the ring also has a positive charge. And I'm just going to label these R groups as R, R prime, and R double prime. So in this case, it's an alkylated ammonium salt. This is strongly electron withdrawing, not due to resonance, simply due to induction, right? That nitrogen's not very happy with that positive charge, so it's going to pull electron density out of the ring. And then the last one is a derivative of toluene, where you've got 3 different halogens coming off the carbon instead of hydrogen. Again, just like we saw with the last one, this is simply due to induction. Anytime you've got a strongly electron withdrawing group, it's going to suck electron density out of that ring system. Does that make sense? Now let's do our moderate ones. For moderate activators, you typically have some sort of pi bond directly attached. So for example, a ketone would be a moderate activator. So if you look at the substituent, there's a pi bond coming off of that atom, that CO double bond.
Activator or deactivator?
Sorry, deactivator. Did I say activator?
Yeah. Yes.
Sorry, shoot. Deactivator. We're talking about deactivators today. So anytime you've got a carbonyl group, whether or not it's a ketone or an aldehyde or an ester, these can all be considered moderate deactivators. The key thing with your ester, though, is you've got to make sure that this oxygen is on the outside, right? If it's on the side closest to the ring, it's actually a moderate activator, not a deactivator. We also have things like amides. But just like with esters, you have to be careful and make sure that that nitrogen is not on the side closer to the ring. We also have things like sulfonic acids, or really any sulfonyl groups. These are going to be considered moderate deactivators. And then anytime you have a nitrile group coming off of your ring, this is considered to be a moderate deactivator too. But the key feature is all of these have this pi bond kind of in this sort of position, right? That's the way I always identify my moderate deactivators. All right, so let's take a look at the regiochemistry here. And I'm going to abbreviate electrophilic aromatic substitution as EAS. But what I want you guys to do is to draw all of the resonance structures for acetophenone. And then what I want you to do is to determine which carbons on the acetophenone are going to be the most reactive for electrophilic aromatic substitution. So I'll go ahead and draw the skeleton structures while you guys are working on that. Clean this up a little. I'm going to kick electron density over like that, and I'll get us started on the first one here. So where are the partial positive charges? What positions are they going to be in? They're going to be ortho, para, or meta? Yeah, if we look at this first one, the positive charge is in the ortho position. If we keep on pushing electron density.
Is it between double bond right there?
Oh, yes, thank you. I forgot this double bond. And then if we keep on pushing electron density around, we can move this charge to the para position. And then we can move that charge over to the other ortho position. So now what I want to do is draw the hybrid structure where we have partial charges. There's also one more resonance structure where you just kick up electrons from the carbonyl. Okay, so we know we've got partial pi bond character in the ring, we've got partial pi bond character here, and we've got partial pi bond character going up to the oxygen. The oxygen has a partial negative. The carbon down here is partial positive. These two ortho positions are partial positive. And then the para position is partial positive. Is this going to be very good at doing nucleophilic attack? Not very good. These reactions tend to be a lot slower because the aromatic ring is electron-withdrawn. It's not going to be a very good nucleophile. Which carbons on the aromatic ring are going to be most nucleophilic?
The ones without partial charge.
Yeah, the ones without partial positives, right? The ones with partial positives are really crummy nucleophiles. In fact, they're deficient of electron density. So, process of elimination says that anytime you've got electron withdrawing groups on your aromatic ring, it's going to be a meta director, right? So these are the most nucleophilic carbons. However, this reaction, like I said, is going to be a lot slower than the corresponding reactions where you have an electron donating group. Does that make sense? All right, there is one weird exception, just like with most chemistry. And this involves halogens. So let's say we've got a halogen on here. I'm going to abbreviate this halogen as X. This could be fluorine, bromine, you name it. Do you think this is going to be an activator or a deactivator? Is it donating electron density or is it pulling it out of the ring?
Pulling it out.
Oh, this is tricky. I don't think it's immediately clear, right? Because you can make an argument that this is electron withdrawing, so it's pulling electron density out of the ring. The other argument could say, well, resonance is pushing electron density into the ring, right? The story is kind of mixed between the two. So if we look at this, halogens are deactivators. Whoop. Meaning the reaction is slower than pure benzene. However, you can draw resonance structures where it's pushing electron density into the system. So even though it's a deactivator, it's going to be an ortho-para-director. So I'll make this big. It's something that's a little bit confusing because we're oftentimes taught anytime you've got a deactivated aromatic ring system, it's going to be a meta-director, but this is the odd exception. Halogens are just weird that way, and we can show this experimentally. Does that make sense? So now the question is, what if you've got multiple substituents coming off of your benzene ring? Let's say you've got multiple activators or multiple deactivators or a combination of activators and deactivators. We have to kind of do some troubleshooting. So let's take an example. Oop. And let's name this molecule first. What would this molecule be named?
Nitrate. Oh, para.
Which one?
Yeah, which one's the parent? Good question. Toluene, right? So toluene's our parent. We've got a nitro group in the para position. So this would be para-nitro-toluene. Okay, and let's try to do electrophilic aromatic substitution. And we'll just do an easy one. We'll do bromination. So now the question is, which carbon is going to be most reactive? Is it going to be this top carbon? Let's say this guy up here, or is it going to be this lower carbon down here? The red one? All right, so let's go ahead and try to rationalize this. All right, if we look at this top group up here, I'm going to erase these. Is this going to be an ortho-para-director or a meta-director? Ortho-para, right? So ortho-para-director. So if we look at it, that means that it's going to favor these carbons. Can we favor that bottom carbon? No, it's already occupied. We can't do EAS on a carbon that already has a group on it. Okay, now let's do the lower one. And we'll say, all right, a nitro group. Is that ortho-para or a meta-director? Meta. Okay. So if we're looking at meta, we're looking at the meta position relative to that nitro group, which again means that the meta position is going to be that same carbon. So if we brominate this, it's guaranteed that that bromination is going to occur at that upper carbon and not the bottom one. So we could put in our CH3, and let's assume we have one equivalent. We can brominate that carbon. If we added two equivalents, we could brominate both of them, right? So we can over-brominate it if we would like. All right. So let's make kind of a list of things to watch out for and a list of rules. First one is identify substituents as ortho, para, or meta directors, just like we did. And then if there's a tie, the strongest activator wins. All right, and then third rule is if still tied, pick the site that is most accessible. meaning the site that's not sterically blocked, right? So I'll give you guys an example, and then I want you guys to try to figure it out on your own, and then check with your neighbor to see if you guys are coming up with the same answer. So for this one, I'll have a nitro group down here. I'll have my methyl group up here. And then I'll have an alcohol over here. And in this case, we're going to do bromination, so standard bromination conditions. So I'll give you guys a minute to work on this and then confirm with your neighbor. All right, show of thumbs if you got it. All right, looks like we got a lot of thumbs up. All right, let's start out with this methyl group. Is that an ortho, para, or meta director? Ortho, para. We've got an ortho position right here. We've got a para position here. The other ortho position is where that alcohol is coming off, so we can't count it. All right, next group. We'll go over here. Alcohol. Is that going to be an ortho, para, or meta director? Ortho, para. So if we look at the ortho position, there's only one there, the other one's occupied, and so is that para position. Okay, now let's do the nitro group. Is that ortho, para, or is it meta? Meta. The only meta position that's open is right there. So now what we need to do is we need to kind of settle this dispute, right? What's the strongest activator? The alcohol, right? That alkyl group is weakly activating, so really it's not going to be a huge contributor, which means that this site right here is going to be the most nucleophilic position on the aromatic ring. So when we go ahead and we do this bromination reaction, we're going to add the bromine over there. Does that make sense? We'll add our bromine here, and then we'll add our OH. All right, so let's go on and let's talk about steric effects a little bit more, because there is a little bit of nuance here. And this is directly related to number 3, where it says, if still tied, pick the site that's most accessible. So steric effects. There's a problem with ortho-para directors. Let's take this example, just toluene, and let's say I brominate it. Which site's going to be brominated? The ortho position or the para position? Oh. Okay, I'll give you guys a minute to chew on that, and then I'll give you a different example. Tert-butylbenzene. Which position's most likely going to get brominated, ortho or para? More para? Why do you think more para?
Sterics.
Sterics, all right. Hence the title of the slide.
Can't get that one back.
So we know that this one's going to be major. You want me to use a glittery pen?
Yes.
Does that make you feel better? All right, for the next one I will. This one's going to be minor, simply because the bromine's going to have a little bit harder time sneaking in that ortho position due to that spinning helicopter blade of the tert-butyl group. When we look at the top one, it's actually flipped, where this one is, where'd it go? There we go. This is major.
Not regular glitter.
And this one's minor. Does anybody know why?
Because on the bottom one it's 3 methyl groups compared to 3 hydrogens. It's just so much
Yeah, so you're saying for the bottom one, it makes a lot of sense that it's going para due to the ortho position being blocked. But conversely, why are we getting more bromination in the ortho position for the top one? What do you think, Sarah? Yeah, it becomes a statistics game, right? If we look at the top one, we've got 2 ortho positions, which means it's more likely to be brominated because that methyl group's having a pretty minimal influence. It's not very big. That means bromination is going to favor that one. So anytime you've got a really, really small activator, like a methyl group or an alcohol, you might observe a significant amount of ortho substitution. However, if that group that's your activating group is anything that's big, it's going to really, really favor the para position. So let's make a note of that. So most of the time, orthopara directors favor para substitution unless your activator is small. So that's a pretty simple rule to live by.
So for the top one, would there have been slightly more than 33% for the having the para position? It might still be minor, but as a percent, like it would have
I would have to look in the textbook to see the actual percentages. Oftentimes it's hard to predict. You have to run the experiment and check it. But I wouldn't be surprised if it is close to 33%. Yeah. All right, let's do a challenge problem. I want orthobromination. I don't want parabromination. How can I do this? Maybe block it somehow? All right, so what I want you guys to do is to come up with a short synthetic scheme and then check with your neighbor. All right, show of thumbs again. All right, I think most people are on their way or close. How do we install a blocking group? What was that? Sulfonation, yeah. And we can do this using H2SO4, and then what was the dissolved gas in there? SO3, so fuming sulfuric acid. That will favor the para position simply due to sterics. Okay. And now we can go ahead and install our bromine because that para position is blocked. So we'll do Fe, or actually Br2 and FeBr3, our iron tribromide. And this is nice for a couple reasons. So let me finish drawing this out. If we look at this top group up here, we know that it's an orthopara director, which means it's going to favor these positions. And then if we look at this group down here, our sulfonic acid, is that orthopara or meta director? Meta, which doubly favors the carbon that we want to attack, right? So if we look at this, bromination is really going to be favorable in that position. All right, and we're close. How can we get to our product? Yeah, dilute sulfuric acid. So you can use this as kind of a nifty trick for getting around any potential regiochemistry problems. Yep.
In an actual experiment, though, will we get a lot of having 2 bromines in the end? Because since we're putting electrobromine and the Fe bromine, won't it do bromines on the other side of the thing?
No, I think I understand what you're asking. So you're wondering if we run into a problem of overbromination.
Mm-hmm.
Typically, you only run into a problem of over substituting something if you're adding on an electron donating group. which makes your new product even more nucleophilic. In this case, we're depending on a bromine, which is an electron withdrawing group, and so it actually slows down the reaction and prevents overbromination. It's a lot easier to control, but great question. All right, so let's talk a little bit about synthesis strategies. This is the chart from our book. We're on Wednesday, right? Look at all of this stuff that we covered. We've got a ton of reactions that we've learned. A lot of really useful ones synthetically, and now we kind of have to figure out a good approach for piecing this all together. The other important thing to remember is if you're trying to add on multiple groups, you have to keep track of these ortho-para directors. There are a couple of important things to keep in mind, though. So let me put this down. So I'll put in two important notes. The first one, I think I actually remember doing this on accident, is let's say I've got aniline and I want to nitrate it. If we look at the aniline, is that going to be an ortho-para director or a meta director? Ortho-para. So intuitively you'd say, well, it is pretty small. Maybe we would get some ortho. Maybe we'd get some para too. However, when you run this reaction, you'll be greeted with tar-like goo. So I'll just put that in. Goo. What ends up happening is you end up polymerizing your aniline and you can't nitrate it. It just simply won't work. In order to run this reaction, you have to install a protecting group on your amine. Usually it's some sort of Bach protecting group, and then you can nitrate it. However, you can't nitrate aniline directly. That's one important thing to remember. The second thing that's really important is, let's say I have a nitro group and I want to do a Friedel-Crafts acylation reaction with aluminum trichloride. Will this work? A nitro group's a meta director. Intuitively, a lot of chemists say, yeah, this should work. But the problem is the nitro group's pulling out so much electron density from the ring. The ring's not nucleophilic enough to really do much at this point. So again, you run into no reaction. So let's make a side note. Strongly or moderately deactivated rings cannot do Friedel-Crafts. I know I mentioned this with the alkylation, but it's true with the acylation as well. So you can't have any strong or moderate deactivators. If you have something like a chlorine or a bromine or some sort of halogen, it can work, but the reaction is a lot slower than you would want. So ideally, you want to try to order your synthetic scheme so that if you are doing an alkylation or an acylation, you do it before you put on any of your strong electron withdrawing groups. That's an important thing to keep track of. So pay attention to reaction order. Try to install electron withdrawing groups last. So let's do some practice. Since I know you guys love synthesis. All right, for the first practice problem, let's try to make this molecule starting from benzene and any other materials that you would like. And oftentimes, you have to do this in more than one step. You have to be careful with the order that you do it, and you have to maybe use blocking groups on occasion. So I'll give you guys a minute to work on this, but check with your neighbor.
We had to start with benzene.
Yep, you start with benzene. That's your ultimate starting material.
Then you get your pair position.
Oops, shoot, sorry. I've made a mistake. My notes. This should be a bromine. We haven't covered how to install alcohols yet.
I was wondering.
I was
Yeah.
gonna do some substitution. Yeah.
We will get there though, just later.
We can do substitution for bromine. There's two of these positions, one of that.
All right, I'll show you guys a little bit of my strategy just to get you started. So what I would do is I would break this down into 3 possible different routes, right? So let's do this green route and say, all right, in the green route, I want to install the bromine, right? Which means that our precursor, if we're going along the green route, must have looked something like this, where the nitro group and the ketone were already on there. And FeBr3 and bromine. Will this work very well? Yes, no, maybe so.
No, it says
That's a lot of withdrawing.
Yeah.
Yeah, not only is it strongly electron withdrawn, but if you look
will both be there.
at this group right here, that's a meta director. The meta position would be right here. The other meta position's blocked. And then if we look over here, that's also a meta director. And the meta position for that one would also be right there. Our bromine wouldn't get installed in the correct position. This is a dead end. So we'll cross this out and say no go. All right, let's do the blue one. The blue one, we're trying to install our nitro group, which means we need HNO3 and H2SO4. What is going on up there? If we look at the ketone here, this is going to be a meta director. So we could favor this position and that position. And then if we look at the bromine, is that ortho, para, or meta? Ortho, para. It's the weird exception, right? So perhaps that could work. We'll leave this on the cutting board. And then let's do our last one. Just so we have options. Okay, so if we do this, will that work very well?
No.
Why not? We've got the strong deactivator, right? So if we look at this, I'll use the rainbow pen. This is a strong deactivator. I don't know if I really like that pen, but
I love it.
all right. So we know that this red pathway is kind of a dead end too, and then let's go along the blue pathway. So the question is, do we want to start with acetophenone, or do we want to start with bromobenzene? Which one? Bromobenzene? Why bromobenzene?
Because acetophenone won't put in, right?
Yeah, if we look at acetophenone, this group right here would favor metabromination, right? We want parabromination. So again, this is our dead end. However, if we do this one, our bromine is going to favor orthopara. Bromine is pretty electron rich. It might sterically block those ortho positions. You might have to purify out some of that, but it's really the best feasible route here. So if you do this, it will work because bromine's only a moderate deactivator. And then we can make this pretty easily from benzene by using bromine and iron tribromide. So you can see we're getting into the the stage of synthesis where it's kind of turning into this strategy game. Don't overwhelm yourself. It's okay to find dead ends and cross them out. At least you've crossed out a dead end. Oftentimes, especially with term 3, people will hand in these crazy synthesis schemes. As long as it works, that's fine. You're welcome to use as much scratch paper as possible, but try to map it out like this and just go stepwise backwards. That's honestly the best route at this point. All right, I think that's where we'll leave it today. Tomorrow when we come in, we'll switch gears and talk about nucleophilic aromatic substitution and then addition elimination reactions.